Hi everyone, today we will make a deep dive into the concept of EMF of a source. Now, NCERT textbook defines EMF of a cell as the potential difference between the terminals of the cell when no current is taken from the cell, meaning when the cell is in open circuit. Whereas if you see some standard textbooks like Electrodynamics by Griffith, there he defines EMF as the work done by a non-conservative force to take a unit positive charge around a closed loop or a closed circuit. Now, which definition is right? Well, both are right, but I prefer the second definition, and the reason for that will be clear as we continue in this lecture. But before we start the discussion on EMF, let me take a similar example but related to gravity. So I'll try to create a motion in front of you. Just see. So you saw that when the marker was coming down, gravitational force is also down. So gravity did positive work on the marker, and that's why the marker gains energy. And when it hits my hand, all that energy is lost to my hand and to the surrounding air. And that's why the marker came to rest, isn't it? Now, do you think gravity will take this marker up? No, right? So if you want this marker to follow a continuous path in a closed loop or a closed circuit, then it is important when the marker is going up, there must be some force which will fight against the force of gravity. And obviously that force is from me. So let me call it force from Pankaj. And now if I calculate the work done to move this marker in this closed path, then I'll get closed line integral. This circle here means I am integrating in a closed path force dot displacement. This is the definition of work done, right? And what are the forces on the marker? Force from gravity plus force from Pankaj. Now notice in this equation that the first term, integral force of gravity dot displacement, is the work done by gravity in a closed path. And since gravity is a conservative force, work done in a closed path by conservative force is always 0. You can see, right, while coming down, gravity did positive work. But while going up, displacement is up, gravity is down, so it does negative work. So they cancel. So the total work done in a closed path by gravity is 0. So whose work done is left? Work done by Pankaj. Right? So this work done in a closed path, if I now divide by mass of the marker, then I can call this GMF, gravitomotive force. Now obviously this is just a bad name which I have given. It is not a force. It is actually work done by a non-conservative force. Remember, my force is non-conservative because in this closed path, work done by me is not 0 because I did work only in this part. That too, I did positive work, right? My force is up, displacement is up. So this positive work done by a non-conservative force per unit mass could be called, if you want, GMF. Now, though there is nothing called GMF, it really helps you to understand EMF. So let's now discuss EMF of a cell. EMF of a cell or battery. So in a cell, you know that there is some electrolyte and there are 2 electrodes. Now, due to some electrochemistry, due to some chemical reactions inside the cell, electrons will be transferred from the rod to the electrolyte and from the electrolyte to the rod, to the other rod. effectively what happens is one rod becomes positively charged and the other rod becomes negatively charged. Now, though this was done by chemical reactions, you can model this by assuming that a positive charge here inside the cell must have felt some force which I will call chemical force, due to which this became positively charged, and therefore this lost positive charge, so it became negatively charged. Or you can effectively say that electrons here felt a chemical force this side, and thus this became negatively charged and this became positively charged. Okay. Now, as these chemical forces separates charges, here positive and here negative, there will be an electric field inside the cell from plus to minus, an electrostatic field, and that will exert a force on this plus q charge in this direction, which is your electrostatic force. So how long these plus charges will keep coming here? Well, initially the chemical force will bring the charges this side, and that will create this electric field, and that will create this electrostatic force, and therefore a time will come when in equilibrium the chemical forces will be balanced by the electrostatic force. Okay, and that is when there will be a potential difference developed between the plus and the minus of the cell, right? Now mind you, these chemical forces are important. Without that, these electrostatic forces would have brought all the plus charge back to minus charge, and the potential difference would be lost. So these chemical forces helps you to maintain potential difference. Now when you connect a wire between the plus and the minus of the cell, what will happen? Well, a current is generated from plus to minus, and in steady state this current will be same everywhere. So I can say in time t, q charge flows everywhere in the circuit, everywhere, okay, in steady state, and the current can be written as q by t. Since it is constant current, no need to write dq by dt, isn't it? Now in steady state I said current will be everywhere same, right? But at the start current may not be same everywhere. However, the surface charges on the wires will make sure that the current everywhere becomes same. Let me explain that. So if I could zoom this part of the wire, let's say like this, and current here is, let's say, I1, and current here is, let's say, I2. Now if I1 is greater than I2, then some charges will be developed on the surface, positive or negative, that depends on the particular case. However, let's say for simplicity, here more positive charge is developed on the surface and here less. So that will create a electric field this way, which will have components this way and this way, isn't it? That electric field component is against this current, so this electric field will decrease this current, whereas this electric field is in the same direction of this current, so this electric field will increase this current. So initially, if this was 10 ampere and this was 8 ampere, just at the start, remember, when steady state has not reached, then these surface charges will be developed on the wire, so that it will create an internal electric field which will make sure that this current is decreased and this current is increased. So maybe after a while both becomes 9 amperes. So this is how surface charges are developed on this wire when you connect the wire to a cell, and those surface charges will create an internal electrostatic field inside the wire, which will make sure that current everywhere is same. Beautiful, right? So now let us carry a charge plus q all round the circuit and see how much work is done, just like in the case of marker. So work done would be force dot displacement, work done in this closed loop. The force acting here is electrostatic force plus the chemical forces, right? Dot displacement. Now, like gravity, electrostatic force is also conservative force. So, outside the cell, the surface charges will create electric field in such a way that everywhere inside there is electric field along the current. And thus, charges are moving this way, electric field is this way outside, so it does positive work. But inside, the plus charges, when they come here, electrostatic force is here, remember. So electrostatic force will do negative work, and that's why these chemical forces are very important, right? Otherwise those plus charges would not come against the electric field. So the plus charges which are brought here by the outside electric field cannot reach here without the help of chemical forces. Just like the marker cannot go up without my help, isn't it? So the first term would be 0 because electrostatic force does positive work outside and here it does negative work. But still there is work done left due to chemical force, isn't it? And this work done, if I divide by the charge which I carry, that is what is called EMF of the cell. So please understand, EMF of the cell basically means that when you take a unit charge all around the circuit, unit charge because I divided by Q, right? This is work done to carry Q charge. If I divide by Q, it becomes work done to carry unit charge. Price of 10 apples, if you divide by 10, that is price per unit apple, isn't it? So EMF is basically work done to carry a unit positive charge all around the circuit, all around the loop. And you know that conservative forces will not do any work in closed path. So there has to be some non-conservative forces. In this case, it is the chemical force. So since it is work done per unit charge, what will be the unit of EMF? So the unit of EMF, the SI unit of EMF will be obviously joules per coulomb. So you can think of EMF as how much energy is given by the cell per coulomb as it goes round the circuit. Okay. So when charge Q goes around the circuit, the battery does E joules of work per coulomb, right? That means 1 coulomb gets this much energy. If 1 coulomb gets this much energy, E joules of energy, then 2 coulomb will get 2E, 3 coulomb will get 3E, so Q coulomb will get QE. Now this energy given has to be used in some other form. So this energy is used as heat in the external resistance of that wire which I connected. However, in real world, the batteries also have some internal resistance. Therefore, a part of this energy given also goes as heat in internal resistance of the cell. So energy given is QE. Heat developed in the external resistance can be written as I square RT in steady state, right? And in internal resistance it will be I square small rt. Now Q itself can be written as I into T because I was equals to Q by T, right? If you cross multiply, Q will be IT. So one I will cancel and one T will cancel. So you will get E equals to I into R plus I into small r. And this quantity is also called potential difference across the wire, the external resistance. So we can write this as V. Remember, this is the useful work per coulomb that we need because this is wasted as heat in the cell itself, whereas this heat can be used for our purpose, right? It could be in electric cooker, it could be an heater, it could be an electric bulb or whatever. So this is the energy given per coulomb, whereas this much is the energy which is actually useful per coulomb. If you divide these two, energy useful divided by energy given by the cell, and that is what is called efficiency of the cell. So in this example, I can write V as I into R, and E can be written from this equation, I common R plus small r, isn't it? So efficiency of the cell would be R by R plus R. And if your battery is ideal, if your cell is ideal, which means internal resistance is 0, then the efficiency will be 100%, right? And I think now you will understand the NCRT definition, which says that in open circuit, so when you keep the circuit open, there is no current flowing, right? In that case, the potential difference across the terminals of the cell will become EMF. Now you may think, sir, just now you told V is potential difference across the ends of the resistance. Well, this was the wire and these were the terminals of the cell, right? Isn't it? So these 2 points are same. So potential difference across the wire is same as potential difference across the cell. But when the circuit is open, current will not flow obviously. So there cannot be any potential difference in the wire because there is no wire. But here there will be potential difference, and that is V, which is also called terminal voltage. Okay. Another way to understand is V is I into R. So your I is equals to V by R, isn't it? So when you don't connect anything, what is here? Air is there. And we assume resistance of air is infinity. So open circuit means resistance is infinity, so current will be 0. But voltage will be some finite value, isn't it? Finite number divided by infinity is 0, right? So that finite voltage across the cell when the cell is in open circuit, that is what is called EMF. However, I like the definition given by Griffith because you will now see that there are some cases where there are no cells only, there are no batteries, but still there is EMF. So you don't need cells to define EMF. Okay. Now let me talk about an example where there is EMF even if there is no cell or battery. And that is what is called induced EMF. So think you have a circular conducting wire and I make the north pole of a magnet come towards the wire. So if north pole is coming towards the wire, then magnetic field will be into the wire like this. And if it is coming closer, then the magnetic field which is represented by B will increase with time. So dB by dt will be positive. And it was found experimentally that as you move the north pole of the magnet towards the coil, a current is created in this wire in this direction. We call this the induced current. So if you are getting current, then obviously if you put a bulb, that bulb will become hot. Some electric energy will be created. But that electric energy, if it is created, then there should be some work done to carry a unit charge all around the circuit. So who is doing that work? Previously it was the chemical forces, right? But here there are no chemistry only. So what is happening? So this is where we make use of Faraday's law, which says that whenever magnetic flux phi, so this phi represents magnetic flux through a circuit, or in this case through this coil. When magnetic flux through a coil changes with time, an EMF is developed in that loop. And as you know, EMF according to the definition given by Griffith is the work done, so force dot displacement per unit charge, isn't it? And on the right side, magnetic flux can be written as B times area. Right? Area vector is here, B is also here. So cos theta no need to write because it will be 1 because theta is 0 between magnetic field and area vector. Anyways, so in this circuit now, because this area is fixed, A can be taken as a constant, so A will come outside. And this force actually is made up of two parts, QE plus QV cross B. But here our loop is not moving, so this is not necessary. So there is no velocity of the loop, and therefore only this is useful. Now you may think, who told sir there is no velocity of the loop? The loop doesn't have velocity, but charges inside may have velocity, you may think. Well, consider a charge q here. If current is going this way, it will have velocity this way. Magnetic field is this way. So the force of magnetic field will be here. Isn't it? The force of magnetic field. However, this force is perpendicular to the loop, and whenever we calculate EMF, we calculate work done along the loop. So this dl is displacement along the loop. So dl is here, magnetic force is here, so it's not going to do any work. So while calculating EMF, this force is not going to be of any use. Therefore, this is useless, and therefore the force by Q, right, force by Q will be what? E. And therefore I can write F by Q as E, which is minus A dB by dt. Please understand that this E is not the same E which we studied before. That was electrostatic field created by charges. This is electric field which is created by changing magnetic field, right? And you can see the work done in closed path due to this electric field is not zero, right? It is not zero. This is the work done per unit charge, right, by the electric field in this closed path, and that is not zero. So what happens is, when magnetic field changes with time, electric field is created everywhere like this. Actually, we should have taken a solenoid to create this magnetic field, okay, but those are details, okay. So here we will just assume magnetic field is changing in a circular region that creates this kind of circular electric field, and therefore if you move a charge along this loop, will do some positive work, and that work done is what is called EMF when you divide the work done by the charge. And since it is not coming zero, this E is non-conservative electric field, and therefore we give a different name to this. We call it induced electric field. Induced electric field, which is non-conservative, created by changing magnetic field. Now we will talk about another interesting source of EMF, which is motional EMF. Motional EMF. So let's say I have a rod, a conducting rod, which is moved with some velocity v perpendicular to the length of the rod, and let's say the length of the rod is L, and there is a magnetic field B everywhere in this region, okay, uniform magnetic field everywhere same, and it's not changing with time, not like the previous example, okay. Now as this rod moves, the charges inside which are free, obviously free electrons are only free, but it is easier to discuss in terms of positive charge. So let's assume if there was a free positive charge here, where it will experience force. Well, because the rod is going this side, this positive charge will also go that side, isn't it? So there will be a force from magnetic field given by V cross B out. So there will be a magnetic force QVB, right? And actually electrons are the ones who are free again, and they will feel force down, because electrons have negative charge, so they feel force opposite to wherever positive charges would feel force. So if positive charges feel force up, then electrons are actually feeling force down. However, the end result is same, right? If electrons feel force down or positive charges feel force up, end result is what? Because of these forces, this end will become positively charged and this end will become negatively charged. This is very similar to chemical forces in batteries. So just like chemical forces separated the charges and made the two rods plus and minus, here the magnetic force along this rod is making one end plus and the other end minus, isn't it? Now once this becomes plus and this becomes minus, there will be one more force due to the electric field. So electric field will be from plus to minus. So there will be an electrostatic force, which is Q into E. And how long this separation will happen? Till in equilibrium, these two forces will balance. And that time QVB will be equals to Q into E. And if I cancel the Q, E will be what? VB. Isn't it? And if you want to know the potential difference, because one end is plus, other end is minus, so there has to be some electrostatic potential difference. So that will be work done by electrostatic force to carry a charge Q from here to here divided by the Q. Meaning it is work done per unit charge. Now, remember you have to use electrostatic force because potential differences are only defined for conservative forces like electrostatic force. And that is force dot displacement. Force is Q into E, it's constant, so no need to use integration, and distance from here to here is the length of the rod. So force times displacement is the work done by the charge. So this is the potential difference, isn't it? And what is E in magnitude? VB. So this is your BLV. This much potential difference is there between the ends of the rod. And right now, since no current is flowing in the rod, because once equilibrium will reach, this movement of charges will stop, right? And since I have not connected any external wire, no current can flow. Therefore, it is like a battery in open circuit. And if you remember in open circuit, I told you EMF is same as potential difference between the terminals of the cell. In that case, here it is terminals of the ends of the rod, and that is BLV, right? However, we should be able to show that we will get the same EMF even if there was some external circuit. So let's try to do that. So let's say we move this rod with velocity v, length L in magnetic field B. So as we learned before, there will be magnetic force pushing positive charges up. So this end would be plus and this end would be minus. And this will now drive charges this way, right? Positive charges would go this way. Actually, electrons would go this way. As I told many times, it is easier to discuss in terms of positive charges. So because of plus and minus of this rod, there will be surface charges developed in this wire, which will create internal electrostatic field and which will make sure a constant current flows everywhere in the circuit, isn't it? And here a plus Q charge would feel force from magnetic field, which is QVB, and electrostatic force Q into E. And outside obviously there will be only electrostatic force. And if you calculate the work done in this closed path, let us see how much you will get. Now, before I continue, there is something important. Because this rod is moving, you can see this loop will change. This loop will keep changing, isn't it? Now, the way EMF is defined is, listen carefully, EMF depends on the loop. So first you have to decide the loop, and then you have to take a unit positive charge all round along the loop, and whatever work is done, that is called EMF. Of course, conservative forces will not do work in closed path, so there has to be some non-conservative force. Now in the case of cell with resistor, the first case, there the loop was fixed, isn't it? And the non-conservative force which did work was the chemical force. In the previous case of induced EMF, there also the loop was fixed. And there, who was the non-conservative force? the force created by the induced electric field, which was again due to change in magnetic field with respect to time. Now here you have to understand that the loop is changing. So therefore we have to find EMF at a given time, at a given instant. So you have to think that at a given time I take a photo, and this is the photo. So now I have to see what is the work done around this loop to carry a unit positive charge, or take Q charge and divide by Q. So that work done would be the EMF. So be very careful about that. Okay. Now the work done in closed path would be equals to integral of F dot dl. Now as you know, in this whole journey there are electrostatic force plus magnetic force, isn't it? Also, there is one more interesting fact which I will mention now itself. This magnetic force, students, is actually a component of magnetic force. A component of magnetic force. Please keep listening to me, something very nice will come out. So this force which you have written here is actually a component of magnetic force. There is another component which will act here. Why? That I will discuss a little bit later. But I don't care about this force right now, because to find EMF we have to integrate along the loop at a given instant. So when I am moving along this loop, dl vector will be here, and the other component of magnetic force will be here. So dl vector is here, the other component of magnetic force will be here, the second component. Let me call it Fm2. Let me call this Fm1. And therefore no work will be done by that magnetic force when I calculate EMF, remember, because EMF is found by carrying a unit positive charge all around the loop in which you want to find EMF. So therefore, please understand that this is not the whole magnetic force. This is just the component of magnetic force which is acting here. Anyways, let's continue. Now the first term is electrostatic force, so work done by that will be 0, it's conservative force, and I'm left with magnetic force dot displacement. So if I continue this, I will get magnetic force is QVB in this direction, dl is along the loop in this direction. Remember, at a particular instant when the rod is here, we are moving along this loop. Now though we have to move along the loop, this force acts only in this part of the rod, because only this part is moving with velocity v like this, other parts are fixed. So this part of the rod is going with v velocity, that's why there was a force v cross v up, isn't it? So this integration has to be done only along this rod. So this closed integral can be now replaced by open integral from here to here, and that will give you the total length of the rod L. And then if you divide this work done by charge Q, that is called motional EMF, isn't it? So this time, which is the non-conservative force which did work? It is this component of magnetic force. And what is the formula? BLV. So we saw that when a rod is moved with velocity v along these rails connected to a resistor, current will flow, right? And we saw the work done to carry a unit positive charge all round the loop at a given time, remember, because the loop keeps on changing. So you have to keep the time fixed at a given moment. You have to assume the rod is here and then calculate the EMF. That is how EMF is defined, okay? And once we did the calculation, we found this is the EMF, BLV, and that much energy per coulomb is given to this resistor as heat, just like in the case of battery connected to resistor. However, there is a big problem, because in class 12 we learned that magnetic force is given by this formula, isn't it? And by definition, this force has to be perpendicular to velocity. And if it is perpendicular to velocity, it is perpendicular to displacement. And therefore, work done by this magnetic force has to be zero. Then how come here there was some work done by the magnetic force? That is why I told the force here which did work while calculating the EMF. Remember, right? So that force is actually what I told, component of magnetic force. There is another component of magnetic force which is also present. So let's try to see how that happened. To understand that is very simple. So when the rod was moved with velocity v, current I was created, and therefore any charge here plus q would have velocity here because of the motion of the rod, but because current is there, this charge must have some velocity here, because current matlab flow of charge. So there has to be some velocity of this charge in the direction of current. Let me call that velocity u. And therefore the actual velocity, when you see from ground frame, is here, is along diagonal, because charge is going here and here at the same time. So resultant velocity of charge is here. So this is the actual velocity of charge. And therefore, when you calculate the magnetic force, it should be the motion of the charge, which is here, V cross V, this side. So this is the magnetic force, the total magnetic force, net. And you can see that net magnetic force is perpendicular to actual velocity. So work done by this magnetic force, the total magnetic force has to be zero. However, if you take the components of this magnetic force, okay, this component is, let's say, Fm1 and this component is Fm2. Then what will be the value for this? Well, that will be QVB, because this magnetic force is because of this V, right? According to cross product rule, V cross B is here. So this is QVB. And this component of magnetic force will be what? Can you guess? QUB. Why UB? Because this force is due to this velocity of the charge, U. So U cross B this side, isn't it? So if you study the actual motion of the charge, which is going this way with time, then magnetic force did not do work. Any electrostatic force will be conservative, so it will not do work. Then who is doing the work which is lighting the bulb here or making this resistor hot? Who is doing work? Who is losing energy? Well, the answer is me. Why me? Because I have to apply a force here. Otherwise, without my force, this magnetic force, this component will decrease this velocity of the rod and the rod will ultimately stop. And once the rod will stop, no motional EMF, no current. So, if you want this bulb to glow continuously, it is important you move the rod uniformly. And if you want the rod to move uniformly, you must apply same force as this force but in opposite direction. Just like the first example where gravity was acting downwards on the marker and I moved it up by applying same force in opposite direction, right? So to move this uniformly, you must apply a force equals to QUB. Okay, so ultimately who is doing the work to light the bulb? It is me. Then what was this EMF? Well, please understand, again and again I told, whenever EMF is found, you have to decide one loop. Here loop is changing, so you have to find the loop at a particular time. So at a particular time when the rod is here, when we calculate the EMF, which is work done to carry a unit positive charge all round the circuit, what did we find? Only this force is doing work, because only for this force displacement and this force are in same direction, isn't it? this force is perpendicular to the path, to the loop at that instant. This force is also perpendicular to the path at that instant. And you may be thinking, what about charges which are moving here? If they are moving here and if there is magnetic field here, then V cross B, they will also feel some magnetic force. Well, that is also perpendicular to the path, isn't it? So therefore, while calculating EMF at a given instant, only this is going to do work. However, in the actual motion, if you consider, when the rod is actually moving, who is doing the work? It is me. Now, if this is really true, then whatever work I have done per coulomb, if that is going into this resistor, then that work done by me must be this, because this was the energy given per coulomb, right? If that is EMF, if that is the definition of EMF as we defined it in the case of cell, then this is the energy given to the resistor per coulomb. Therefore, I must be able to show you that during the time the charge goes from here to here, when my force acts to counter this force, the work done by me has to come equals to BLV, of course, per unit charge, because this energy is given per coulomb, isn't it? So let's try to show that. So let's say your rod is here at a particular time, and by the time the charge goes from here to here, let's say the rod has reached here. So this is the x distance and this is the y distance, which is nothing but the length of the rod. So by the time charge went this way, this is your x displacement, this is your y displacement. And my force was acting in this direction, isn't it? And one component of magnetic force was in this direction, against whom I am doing work. So this is my force. So the work done by my force will be F Pankaj integral dot dx. And since x and force by me are in same direction, no need to write cos theta. And what was my force? Well, that was same as this force, which was QUB, right? UB. So this was QUB into dx. So now during the time charge went from here to here, x will be equals to Vt, because remember the rod was moved with velocity v. So this displacement is due to this velocity. Whereas this displacement, which happens along the rod, is due to the velocity given by the flow of current, right? Which was u here, isn't it? So y will be what? Ut or L. Okay. So if I eliminate t from here, I will get x by v equals to L by u. So x can be written as Lv by u, isn't it? Here everything here is constant, so you can take it outside. Integral dx will be simply x from this instant to this instant, isn't it? So now for u, I can write from here, if I cross multiply, what will be u? VL by x. So u will be VL by x, b times x, x cancels. This is work done by Pankaj sir. Per unit charge, if you do, lo and behold, you get the same motional EMF. Wonderful, right? Now finally, if you think I was the one who did the work actually, then what was the use of these magnetic forces? Well, please understand, though I am the one who is pulling the rod and doing this work, I cannot push the charges inside the wire to make this resistor glow, isn't it? So I need these magnetic forces so that my work done on this rod is transferred to these charges through magnetic force, right? So the design of the circuit is done in such a way that as I do work, so let's say I do 10 joules of work, to kill this minus 10 joules of work, isn't it? Because as the rod goes here, if I did plus 10 joules of work, this will do minus 10 joules of work, isn't it? Because it is opposite to displacement, isn't it? So this is the second component of magnetic force. And therefore there was this component of magnetic force Fm2. So if this does minus 10 joules, this must do plus 10 joules, because overall work done by magnetic force has to be 0, and therefore this 10 joules of work done by magnetic force is transferred to this resistor as 10 joules of heat. Okay, so though I am the one who is losing 10 joules of energy to make this bulb glow, understand, without the help of these magnetic forces, it would be impossible for me to use my force and make charges move inside the wire. So that's why this whole arrangement is very beautiful, and I really enjoyed making this video. So I hope you all liked it. Thank you.